Just real quick here, let me take care of something here. Siri, set a timer for 40 minutes, please.
Okay, your timer is set for 40 minutes.
Thank you.
My pleasure, as always.
She is wonderful, isn't she? So there we go. That's now we're cooking with gas, as they say. So yeah, let me just check this one more time here, guys. Making sure that I'm doing this right. Get out of that. Stop that. Okay, here we go. Now, we're going to pick this up, guys, where we left off. And that's going to be here on the fuel system. So I want you guys to take a look here, fuel system wise, take a look at 7-30, 7-30. And when you look at this, this is going to show a couple of different ways that you have to get fuel out of your tanks into your engine, which is, you know, kind of where you want it, I suppose, you know, at some point if you like, you know, a running engine. You look here at the top, you see a gravity feed system. So in other words, a gravity feed system, if you think about it, you know, we want, you know, trying to let gravity be our friend. How does that happen? Well, if you have something that's up here, you have a certain amount of potential energy because it's higher than something else. And then as you release that, then that potential energy then becomes kinetic energy as it moves further down and comes down into the system. So you have an easier pathway for that fuel that is like in a high wing airplane to get down to the engine. Then you look at the bottom one, and what you see is you see more of a what they're referring to as a fuel pump system. And this is the type of thing where you may have a low wing airplane and you need to get that fuel from the wings, the wing tanks of that low wing airplane up to the engine. And there's a couple of different ways that you can do that here. First of all engines will have some form of an engine-driven fuel pump. And it doesn't matter if it's a high wing or a low wing airplane. You're going to have some form of an engine-driven pump that will assist you in getting those, getting the fuel where you want it to go. Now in this case, if you look at the selector valve, you'll see that there are a couple of different positions. You have an off position, you have left, you have right, and you have both. In Cessna aircraft, and I don't know if it's specific to Cessna, but it seems like most high wing airplanes have this feature where you can turn your selector valve to both. And that allows the fuel to come from both tanks sort of simultaneously and just having the ability to pull from both tanks at the same time. And that's, you know, it's a pretty good way to keep your fuel balanced. Now in low wing airplanes, it seems like they have more of the systems where both is not necessarily an option. You can see here that both is an option here on this switch configuration. However, in the Diamond DA40, there is not a both option. There is left, there is right, and there is off. And you kind of want to be careful that you don't select that off position or, you know, that silence will get your attention. So again, here we go. You can see these things here. Here's the fuel, etc., and kind of how it goes through. You have a priming system that allows the fuel to go into the cylinders to start the engine. You have a carburetor here in this case, or if you don't, you have a fuel injector. You have a couple of different types of fuel filters just to kind of keep any sediment or any contaminants out of the engine itself. And here again, you have kind of the same thing. This one is showing an engine-driven fuel pump, but the other airplanes are going to have an engine-driven fuel pump as well. And then you also have boost pumps. Boost pumps are going to be an electrical-driven pump that will assist that fuel pump in feeding that fuel into those engines at certain phases of flight. In the Diamond, if you get above 12,500 feet, you're going to see a little indicator that'll pop up on your annunciator on your primary flight display. And what it'll say is it'll say something to the effect of, oh, I'm trying to remember what it says. Something like fuel something. It's some kind of little bubbles that can form in the fuel as that fuel is being pumped from the fuel tanks toward the engine. And in some cases above 12,500 feet, you may have to turn on your electrically driven fuel pump just to keep the pressures correct in there so that you get good fuel flow into your engine. And then some airplanes will have a low boost and a high boost. And depending upon the phase of flight, you may switch from one to the other. So that's kind of how the fuel systems work in most airplanes. I talked about that fuel selector valve here also. The fuel selector valve allows you to go, here you go, in the left, in the right, or in both. So yeah, that's kind of how that works. And they'll have certain little things that they may have written on that fuel selector valve, just kind of depending upon the airplane. Fuel gauges, a lot of times fuel gauges, they'll kind of work in kind of a float system type of a thing, where as you fill the tanks, there's an indicator that kind of rises with the fuel as it's added, and then it lowers. And then that type of a float actuator type of a thing then in turn moves a little needle inside the airplane in your fuel gauge to kind of show here's where your fuel is. The actual old analog needle type fuel gauges, they're not very, well, they're not as reliable as the new digital presentation of those fuel gauges. Because it used to be that you'd have these older type of fuel indicators, the fuel gauges inside your airplane. And you could have a reading where you had one tank where the needle is way over here and another tank that may just kind of hover in the halfway point, when you have just looked in both tanks and you know both of them are full. Well, again, you kind of have this little float thing, this little mechanical device that kind of sends that, indication to the actual gauge itself that doesn't really work all that well. And in some cases, you'll have and this is the worst scenario, where you show that you have fuel that you actually don't have. And it's where those gauge kind of stick. You guys have seen those old movies where you see the pilot tapping on the fuel gauge like there, and then all of a sudden you see the needle go, meh. And that's, of course, not good. It's one of those things where in those older style of airplanes, you always did something that we called stick the tanks. What that means is that you have a stick. Yeah, I'm talking about like a piece of wood. And on that piece of wood, you're going to have these markings on it that indicate the gallons for this particular airplane. And what you would do is that you would get up on top not on top of the airplane, but you'd climb up on the strut, get where you could get to the actual fuel filling cap, take off the cap, and you'd put that stick down, and then you'd pull it out, and you'd see where the fuel mark was so that you could know how many gallons of fuel that you actually had. That's the way that you used to track it. You would track it with that, and you would track it with time. Over time, you would learn what your fuel burn is at particular power settings, and then you would actually have a timer, and you would know that in an hour and 42 minutes, I'm out of fuel. One of those things. And so that's kind of how you did it. That was the more reliable way versus relying on these old analog fuel gauges. Now, in the G1000, everything now is digital. And so you have all different types of aids to help you with the amount of fuel that you're actually using and the amount that you have left. First of all, when you fill the tanks, you know that you've got the tanks filled. When you turn your airplane on your multi-function display, you're going to have a thing over here that will allow you to reset your fuel. So you will then ultimately press a button that will reset your fuel to full. You can adjust that. You can say, okay, I want to pull a gallon out because it wasn't quite tippy top. And so instead of saying that you have 51 gallons in your airplane, you could say that you have 50. Or you could take another gallon out, 49, to kind of adjust for that as you saw fit. And it's kind of a conservative way to do it, so that you would say, okay, I know I have at least 50 in here, but I'm going to say 49 just in case I'm a little bit off. And that's kind of how you can do it. Then you have a fuel totalizer that will ultimately meter that fuel as it flows from the tanks into the engines. And that's pretty doggone reliable. Over time, you're going to get a sense of how accurate those electronic or the digital systems are. And one of the things that I have found is that with the G1000, I have never really been much more than about 2/10 of a gallon off in the calculations once you start working with that fuel and knowing what you had to start with, knowing what you had when you finish. How do you do that? You have the lads come down from Atlantic Aviation in Aspen. We love you, Atlantic Aviation in Aspen. And you have them fill up your airplane. Okay, how many gallons did you put in? Okay, I started with 51 here in the tanks. They put in 30 gallons. How much did I actually use? 51 minus 30, that's going to be, what are we going to say here? Let's say 21 gallons. There it is. I used 21 gallons and I flew this amount of time. I had this amount of time for taxi, this amount of time for run up. Here's my climb out, here's my cruise, here's my descent. And you time that, and then you can say, okay, at this power setting, at this altitude, for whatever it's going to be, I burned X number of gallons per hour. To give you an idea, in the Diamond DA40s, at kind of a cruise, well, let's see, we call it kind of a training power setting, and at 10,500 feet, you're burning somewhere between 8 and 8.5 gallons per hour. So that's pretty good. When I'm flying and I'm cruising and I'm going somewhere, I'm closer to 18 gallons an hour, but my engine is quite literally twice the size of the Diamonds. So that's kind of why you're burning more fuel. Plus, I have turbochargers, so I'm able to burn more fuel and to go faster. So anyway, that's kind of the way that the fuel system things work. You got to remember that in your fuel, we burn 100 low lead. That is about the only aviation gasoline that remains available to us to use. They're actually looking to change that. They're looking to to get that lead out of the fuel. The lead is an additive that kind of helps the engines, and the engine manufacturers kind of like that because there's a lubricative quality of that lead in there. But we're actually looking at taking lead out of aviation fuel. Don't know exactly when all that's going to happen, but we're going to find out. Some other fuel options that they're looking at creating fuel from algae, if you can believe that. There are these great big algae farms that they have out there where they're using this algae and converting the algae. I don't know if it's the algae itself or it's one of the byproducts of algae growing that they pull off of that and they create a fuel. And so yeah, there's all different types of options that they're looking at. So stay tuned for that. So now we're going to look here, fuel grades. This is that thing I was telling you about. This is, again, guys, one of those back in the day stories where when I was flying, when I first started flying, I should say, these were the options that you had available to you. If you look, you had an 80 octane, you had a 100 octane, you had a 100 low lead octane, and then you have something called Jet A, jet fuel. Jet fuel is, in essence, it's kerosene. It's kind of a derivative of diesel fuel. And so that's kind of what you have there. The one thing that I want you guys to note is that the higher the number of octane, the more, well, I'm not going to say the less stable, because stable has to do with an ability to break down. But this, the higher the number, the less the volatility. And what that means is that the fumes coming off this 80 octane, which is similar to automobile gasoline, the fumes themselves are extremely volatile. This is why they have these signs out there on these pumps saying, turn off your cell phone. Just the electrical discharge coming from your cell phone could be enough to ignite the fuel vapors coming from those lower octane fuels. Whereas when you look at kerosene or Jet A or diesel fuel over there, I have heard stories, I haven't actually done this, but I've heard stories of guys that would take a container of fuel, open it up, and they would throw a lit match into that fuel, and the fuel would put it out. So again, guys, do not try that at home, okay? But it's a less volatile mixture. The less volatile the mixture, the more you can control the actual fuel burn inside the cylinders itself, inside that combustion chamber. And you can create more power with that. It's why certain automobiles, certain high performance automobiles require a higher octane fuel, is so that it's not as volatile. They can do more with the actual burn inside the cylinders of that engine and create more performance for it. It's very similar to the type of fuel that we use in airplanes. Automobiles, by and large, for just like a regular old, bottom of the line Chevy, the engines in those cars, they aren't really built to the same specifications that airplane engines are built to. We used to call that back in the day blueprint engines, where the tolerances are really, really tight. The difference is going to be is that, those cars, the lower line cars, they have more slop kind of built into those things. They're okay, but they're not going to be real powerful. In the aircraft engine, we want something that's going to produce some power in a lightweight package. And so with that, the tolerances are going to be a lot tighter. To do that, the performance that is required in those requires a higher octane fuel. That's where we get the 100 low lead gas. So that's kind of where that comes from. Some of the things that can happen with fuel from a contamination standpoint that you want to be careful about is, as older airplanes that come from a, let's say, a wet climate, I don't know, like, New Orleans, let's say, and they're stored outside, there's a lot of humidity in the air, there can be a lot of condensation occur inside those tanks, which is one of the reasons why that people who live in high humidity areas, after every flight, they will refill the tanks with fuel almost immediately, and they will not let an airplane sit with air in the tanks, because as the temperatures rise and fall and the humidity in the air, what will happen is that humidity or moisture will form inside the tanks, meaning you have water in your tanks. Well, water and metal ultimately will lead to corrosion. And so sometimes you will find that in older airplanes, when you sump the tanks, and sumping the tanks, if you remember, that's that little siphon thing at the low point of the wings, where you put the little device in there and drain off some of the fuel and inspect it for the proper color and inspect it for any kind of debris. Well, the old airplane that I used to start flying with, it was just kind of a rite of passage. You'd put the strainer in there and you'd get this lower portion here of just rust in there, and you'd have to with an EPA approved disposal method of basically just throwing the thing out in the air. We don't do that anymore. We actually collect that and let it just in special containers, and we let that fuel just kind of dry out. What's the word I'm looking for? I can't think. I need more coffee. That's what I need. Hang on, right here. There it is. Oh, yeah. Evaporate. We'd let it evaporate. Thank you, coffee. And then it would just kind of you'd have all that sediment down in the bottom of these containers. And it would take a while before you could actually get a clean sample such that you would feel comfortable flying that airplane. Well, we don't do that anymore because we have, relatively new airplanes for you guys to fly. And that's one of the reasons why. So that's kind of how, we would do it. And one of the things that you look for, you also want to make sure that you've got the right type of fuel. Remember, using a lower grade fuel than is required, that can lead to detonation. And that's a systemic thing. And then the leftover carbon deposits inside the cylinder itself and those deposits on those spark plugs can lead to pre-ignition. Those are things that we talked about there before. Okay, on with more fuel stuff. Fuel icing can happen. We have to be careful with making sure that we don't have any water in the system at all, because that can also lead to some prevention, you guys can look at that. Refueling. One of the things that you'll notice is that whenever someone refuels an airplane, is that you have to connect this little clamp to some piece of metal on the airplane to quote unquote ground the airplane. And what that does, as an airplane flies, and as basically anything moves around, anything time that there is friction with the air molecules, you can develop a static electricity around whatever that is. You guys have all done it. You shuffled your feet along the carpet, reached over to somebody and kind of touched them, and that basically releases that electrical static piece and it shocks them, right? Okay, that little static discharge thing. Well, imagine if that static discharge were to happen when you were refueling an airplane. Boom. And of course, I think we can all agree that would be bad. So what they do is you pull out this metal line. It's a kind of a braided metal cable that has this metallic alligator clip on it. Pull that out and you connect it to some form of metal on the airplane, and that takes that discharge away so that there's no static electricity around when you refuel the airplane. You'll see the guys at Atlantic, again, we love you, Atlantic, that come and bring the fuel trucks out and they refuel the airplanes. The first thing that the guy does, or girl does, is they pull that cable out, connect it to the airplane, then they pull the fuel hose out. And they have that connected to the truck and connected to that area that's carrying the fuel because they want no static around that at all. When you self-fuel, meaning when you fly to an airport, there's no truck, but over here on this side of the tarmac, here's a fuel pump. And you go over there and you kind of taxi your airplane around, being careful not to hit the tank with your wing. That'd be bad. And so you pull over by this fuel, and then you want to get fuel. So you start entering in the information on the keypad, you put your credit card in, but it will not allow you to dispense any fuel until you have connected, and it senses that you have connected that ground wire. So that's the only way that you can get fuel, and it's kind of a fail-safe that they have with those fuel systems. So you kind of want to be, don't say kind of, you definitely want to be careful when it comes to making sure that you don't have any of that static electricity around the airplane. Heating systems, we talked about that with the, excuse me, when we were talking about the engine. On the fourth stroke, the exhaust stroke, we have the byproducts of combustion that leave the cylinder in addition to heat. That goes out an exhaust pipe. That heat is then captured in this manifold, or this hollow metal tubing that goes over that plate, goes over the exhaust pipe. It doesn't touch it, but it's just over it, and it captures that heat, and then of course through that hollow space in that manifold, that air can be pulled through that manifold and vented into the cabin to keep the cabin warm. Now, let's say that you have a multi-engine airplane, and now you got the engines out here instead of right here in front of you. How do you do that? Well, you have a separate heater. In the Seneca, the heater was called a Janitrol heater, and it's just a special little combustion unit that you have, a little engine kind of a thing, that sat in the back, in the aft compartment of the aircraft itself, and the fuel was fed to this heater from the left tank, and you would turn the heater on, it would start this little combustion chamber, and it would warm up the air, and it would pump that air into the cabin. Well, you had to be really careful about carbon monoxide coming in there with that as well. So, you know, that's kind of what you had, but you had a separate heater. Early on, there used to be issues with those heaters kind of catching fire, and that's just a bad thing to have happen in an airplane. But they've gotten a lot better now. They've got a lot, different types of emergency systems that they have in those things, so that they don't do that as much anymore. And remember, I also told you that some aircraft will actually use an oil cooler so that it would cool that oil, but it would take that heat coming off that oil, and it would actually use that as a manifold to pull that warm air into the cabin. So that's kind of a way to get heat into the cabin. Bleed air systems, turbojet, turbofan, turboprop engines that use a jet type configuration will have an air bleed system where they'll have some of that heat coming off one of the hot sections of that jet, and they'll use that to not just heat the cabin, but it'll also heat the leading edges of your wings and everything on your tailplane for de-ice also is kind of how they'll do it. Okay, now we are starting on the electrical system. When we think about the electrical system of the airplane, we realize we have to have electricity. Where does that electricity come from? Do we just carry a bunch of batteries up there and just do it that way? Well, we definitely have batteries on the airplane, but that's not their job, because if we drained off the electricity of those batteries to power all of our electrical systems, it wouldn't take long for all of those things just to run out of electrons, and then, you know, now what? So you have to have some way to actually generate electricity while you're flying. So to generate that electricity, we use something called an alternator or a generator. What an alternator does, it's a machine. It's got these copper wires in it that will ultimately spin, because there's a belt that's on the front end of that alternator that then is tied to the mechanism of your engine, and as the crankshaft is spinning and the flywheel is spinning and the propeller is spinning, that belt is attached to something that's at the front of that airplane that will actually run that belt around on this system of like these little pulleys and run that generator, so this copper wires spin in here, and when that thing spins, it creates that electricity that helps power all of the systems on our airplanes. So while that alternator is operating, while the engine is actually turning, not the engine is turning, but the crankshaft is turning, it generates that electricity. So that's kind of where that electricity comes from. So you have another system on an airplane. And so these are things here that provide the electricity. So we'll talk about where that electricity goes, how we can control it, and then what do we do when that electricity is not available to us. So that's what we're going to talk about. I want to show you just a little bit here, kind of what we're looking at. One of the things that you'll see here is that you'll see that your aircraft system comes with either a 14 or 28 volt DC electrical system. It is a direct current as opposed to an alternating current. And like your house is going to be AC, your airplane is going to be DC. When you look at this, we'll talk about these things. We'll talk about the battery. We'll talk about a master/battery switch. We'll talk about the alternator/generator switch. We'll learn about buses, fuses, circuit breakers, voltage regulators, ammeters, load meters, and associated electrical wiring. So there's quite a bit to it as it goes through here. The thing that we use the electricity for, clearly on a G1000 equipped airplane, we got a lot of electrical equipment up there, don't we? So we've got to have the ability to bounce a bunch of electrons around. So we have that. We also have lights that we have to power. We've got our instruments, radio equipments, engine gauges, fuel pumps, the electrical fuel pumps, pitot heat, and to even start the engine. So when you look at these things, this is an example here, and you can see this on figure 7-34. What this does is that this shows you kind of a simplified, and I'm emphasizing the word simplified, electrical schematic to show how everything here works. And I think if you look at this, you know, it's easy to kind of go cross-eyed when you look at this thing and just kind of go, holy buckets, how does any of this stuff work? So one of the things that we're going to do is we're going to look at electricity a little bit different. I want to show you here just real quick. This is what we call the master switch. The master switch actually is a series of two switches. You have one that actually turns on your alternator, and you have one that turns on your battery. It doesn't really turn on the battery as much as it allows access to the battery. Flipping both of them up into the on position is considered turning on the master. But we'll talk about when you would want to use which side of this switch for what purpose. So now what I'm going to do, I'm going to show you something else, because one of the guys that has been, he's kind of been a hero to me for a long time, is a guy named Rod Machado. If you guys start reading the aircraft magazines, AOPA, he does a lot of instructor type of columns and articles. He does a lot of speaking. He's a funny guy. He's forgotten more about aviation than I may ever know, but he's just, he is really great. He was extremely helpful to me when we were starting Sam's Academy down in New Mexico, and very, very generous with his time and his thoughts and his effort, creating some of the matrix that we actually use today in our training program, and that comes from Rod Machado. So Rod, I want to thank you, and thank you for allowing me to use what I'm about to show the kids here. So one of the things that Mr. Machado does is that he tries to simplify things, because he knows that not everybody who wants to become a pilot is an engineer. You know, you may not be a mechanical engineer, you may not be an electronic engineer, or have this innate knowledge of all of these systems that we talk about. So he does a great job of simplifying things. And in simplifying things, another thing that he does is that he uses analogies that we're probably more familiar with. And in this case, with electrical, did I put the emphasis on the wrong syllable? He uses, when he talks about the electrical systems of the airplane, he actually uses water to kind of describe how things move, and things having to do with plumbing. We kind of all have an idea about plumbing. We have a water source. In order to get the water source from here to the sink when I wash my hands, we have to have a pipe, right? We probably have to have some kind of a pump to actually move that water. We know that the pipe is only going to be so big. And we know that if that pump puts too much in there, you can put too much pressure in the pipe with too much water, and the pipe breaks or something. You know, so that's kind of how he does it. So I want to show you this presentation that he did, because this, I think, does a very nice job of talking about how the electrical systems work. Now, when we look at this, one of the things that I want you to kind of be aware of here is that this is probably going to go over into the next video, because I do this in like 40-minute videos in each one. So it's probably going to go into the next video, so we're not going to get it all done on this shot, but I just wanted to kind of let you know that. So when we look at the water analogy of electricity, we have a couple of things that we need to know what they are. First of all, you see volts, okay? You're going to see something here that we call volts. And then you're going to see something later on called amps or amperes, or something referring to amperage, okay? So the water analogy of electricity uses water to represent the flow of electricity in a circuit, and pipes to represent the wires. Water pressure represents the amount of voltage in a system. And the amount of water actually flowing within the pipes represents the electrical current within that system. So if we look at this, so here you have, in essence, you have the same pipe. So here you are with the same kind of a wire. Well, when you have a 12-volt system here, you're looking here at basically like 5 gallons an hour. Under a 24-volt system, you can actually run more water through it. It's the same size pipe, but you just have more current running through it than you did before. So you can see here less water, less current, and you can see here more water or more current. And that's going to be the difference between a 12 volt and a 24 volt system. When you see these things on these systems, one of the confusing elements is that you will also see a reference to 14 volt and 28 volt systems. And you're thinking, what the heck? The 14 volts and the 28 volt systems, they have to do with the max amount of that current, that voltage that can be running through those wires. It won't use it all. And in fact, you'll notice here that in this, where it shows this pipe here, you'll still see a little space. That's the 24 volt side of things. The 28 volt is more current, which is the max those wires can take. And it also allows that electricity to flow into that battery, the main battery, to keep it charged. We haven't talked about that yet, but we're gonna. So that's kind of one of the things. So when you see a 12 volt system and then they talk in the same breath about a 14 volt system, it's the same thing. And then you'll see them talk about a 24 volt system and a 28 volt system. It's the same thing. Okay, so just keep that in mind. Now, as we look at this, here we go. We're looking at 24 volt battery pressure. This is what we're looking at. So when we look at this, at 24 volts of electrical pressure, only 20 amps of current can be pushed through this wire. So you have 20 amps. So the voltage is the overall capacity of the electrical pressure that's possible inside this wire. But the flow of this is represented, it is the amps. So if you think about the volt here as the wire itself, and you think about the amount of water in there being the amps, that's kind of what we're looking at here. So as you look, you have a 24 volt system, and here you have 20 amps being pushed through this pipe or this wire. Here again, you have 24 volts, and you can see it's the same wire, but in this case, you can see that that water level is lower, and in this case, only 10 amps are being used. And then down here, you can see here's the same system, and in this 24 volts, you get 20 amps of current, or the water, in this particular line or pipe flowing through here. The point here is that you don't have to use all of the max capacity of this line. And it's probably best that you don't, because what will happen is, even in the most elegant of circuits, you can still have something that can happen that causes that momentary spike in kind of that amperage piece. And you need a little room in there still to kind of allow for that without it tripping the breakers. And we'll talk about what the breakers are here in a little bit. But that's kind of what we're sort of talking about. So as you look at this, it's kind of important to sort of remember, you know, that even though we talk about a 24 volt system and you have 20 amps through there, you can still see there's a little bit of room kind of up there, and that's sort of what you want. Most aircraft systems, when they're running on a 24 volt system, which is the most common aircraft wiring system that they have out there, using a 24 volt system, when you have everything turned on, you're basically drawing only about 16 amps in that 24 volt system. Now again, remember, it shows here on these pipes that 20 amps is kind of the max that can flow through that. 16 is about what you're running when you have everything on, okay? So there's that. Now, let's take a look. Now, if you look here, if you look at this diagram here versus this diagram here, which is just a little bit easier to kind of understand? I'm with you. I like that one. So with this, here's kind of how this works. So when you look here and you think about water, What you can see is that you've got the water kind of coming in here, and you can see that you have this little guy right here. They're calling it a water pump. But the electrical analogy here is this is kind of your alternator, okay? So you've got this device that is creating these electrons, and it's actually then sort of creating the water, okay? In this case, certainly creating the electricity. It flows through here, and it goes to something called a primary bus. We'll talk about that here in just a second. You can see these little things that say CB on here, and we'll talk about those here in just a second. So guys, that's going to end the first segment. Part 2 of that is going to come up here in just a minute, okay? So we're going to pick this back up here on this particular diagram. More in a minute.